Alright you guys, this is video E3.2-8, really the first assignment here in the E3.2-C learning target, which is describe the differences between oceanic and continental crust, including density, age, and composition. So we have these things and they are a bit different from one another. So you should be looking at your sheet of notes here, and again I'm going to move over to the PowerPoint. This one will be a quick hitter. Alright, here we go. So first off, and I already have written in there in italics, crust is the uppermost layer of Earth and part of the lithospheric plates. We call our tectonic plates lithospheric plates, really to distinguish that they are lithosphere and not just crust. Crust is just really the top half of those lithospheric tectonic plates, because remember, lithosphere is crust and that rigid upper mantle that acts just like the crust. It's brittle, it likes to crack and break when it tries to move. So, one, there are how many types of crust? Well, there's two. Whoops. Go ahead and write in a 2 up here. Guess I forgot to do that. And then pause if you need to and get this written down. Oceanic crust is the crust under the oceans. It's thinner, denser, younger, it's more compact. And we'll see that in that picture just below where you're writing this. Continental crust is really kind of the opposite of that. The continental crust is just a land that we're seeing on Earth, but it's thicker, less dense, and much older. The reason it's much older is it says down here, crust is constantly being created at divergent boundaries and destroyed at convergent boundaries. This would be subduction zones, really where oceanic crust is meeting continental crust, and because it's more dense, that oceanic crust is subducting underneath the continental crust. So oceanic crust is far more active than the continental crust, which is why it is younger than any of that continental crust that we're seeing. And in this diagram here, we can really even see that, wow, look how compact that is underneath the weight of our oceans. In addition, we're going to find out here in a second, it's also a different material. But please also notice how this right here, all this would be probably our tectonic plates. And it is displacing that asthenosphere. Okay, we already talked about this, kind of how ice cubes displace water. This particular diagram is a great one. It's showing us lots of stuff. It's really showing us all these features that our tectonic plates can create. So first off, we're seeing that then in comparison to the continental crust here, sort of this lighter gold up here compared to the oceanic crust, which is gray. And over on this side, we are seeing a subduction zone. Okay, right here it's saying this is a convergent boundary, but we have continental crust to continental crust colliding and forming these folded mountains. On the right side here we have a subduction zone. This is where the oceanic crust is subducting underneath, it's getting pushed underneath the continental crust because this oceanic crust is more dense. When that's happening, see, it's being created here at seafloor spreading, but then recycled here at subduction zones. It's this friction that is causing the volcanic mountains on the continental side of those subduction zones. A great example of this is the west coast of the United States with the Cascade Mountains. That is a volcanic mountain chain. We have, we have Mount Shasta, we have Mount Hood, we have Mount St. Helens is probably the most famous or infamous of all those volcanoes. But this is kind of neat because it's showing us a lot of these processes. Okay, and please notice also it says the lithosphere. It's the crust and this, I don't know, maybe that's more of a gold color, this darker gold color, is the upper mantle, which acts just like the crust. Okay, and it's all floating on this asthenosphere down here. So, I want you to fill in that table in your notes. We have the two types of crust, continental and oceanic. And this is showing us all those things we need to know: the average thickness, age, and the major components. What's it made of? So first off, continental crust, anywhere from 20 to 80 kilometers thick. Depending on where you're at, are you close to volcanic activity, are you not, are you close to the edge of that continent, or are you not, etc. Average age, 3 billion years. We date rocks through radiometric dating. Really, that is when that rock is formed. Doesn't matter what type of rock it is. When it's formed, it sort of locks in those radioactive materials that it has in it, and they start decaying at a constant rate. We take the ratios of those materials in those rocks to figure out how old it is. Scientists have been doing this since the 1950s. Carbon dating, on the other hand, is really only for things that have living material in them, because all living things take in carbon as they're living, and when they die, it starts decaying because they can no longer take it in. So 50,000 years or less is really how we date those things. But continental crust is granite. This is very important. The video you're going to watch next sort of shows us the differences between granite and basalt. This oceanic crust is basalt. Oceanic crust is also, you see this big difference, about 10 kilometers thick. And generally 70 to 100 million years. That's a big, big, big difference. The reason this oceanic crust in some of our ocean basins is being recycled all the time. That's it for these notes. Check them out again if you need to.